Welcome back, and in the last video we talked about the idea of monotonicity, whether it's increasing or decreasing, and then boundedness, right? So now we're going to introduce you to the major theorem that allows us to conclude convergence of a sequence without actually having to find its limit, okay? But first, a very nice axiom that we're going to make use of in the proof of the theorem is that if we have a collection of real numbers that's non-empty, then we can say that and if the sequence has an upper bound, or the set has an upper bound, then we can actually identify the least upper bound. So, for example, the set that is the sequence, I don't know, let's say an is a sequence of -1 over n plus 1, right? Then this would have an upper bound, so an upper bound could be 2, 3, 4, right? All those are greater than this sequence, but actually the least upper bound in this case is going to be 1. It's going to be the value that is an upper bound but lower than all the other upper bounds. I digress. Okay, monotonic sequence theorem, major player in the section here, but it says every bounded monotonic sequence is convergent. So in order to say it's convergent, right, we need to satisfy condition 1, condition 2, and then we can say that it is convergent. Okay, I feel the need to go through a proof of this because it is so important. Okay, so this is a very nice theorem that you will see later on in life, but here's how it's going to progress. So a proof, we typically start by stating our assumption. So we let the sequence an be bounded and monotonic. We don't care if it's monotonic increasing or decreasing, okay? But we're going to say for this case that it's increasing, bounded monotonic increasing sequence, and the proof for decreasing is similar. Okay, let S equal the limit of an. Okay, so we've defined kind of that boundedness. Okay, all right. So now by completeness, by the completeness axiom, an has a least upper bound. And we call it L. Call it L. Okay. If L is the least upper bound, okay, then for epsilon greater than 0, L minus E is not an upper bound. An upper. Okay. So then there is an n, a capital N, such that that nth term of the sequence is bigger than L minus E, right? So it's not an upper bound, therefore we can find a sequence that's a sequence value that is bigger than it. Okay? And therefore, and an is increasing as a sequence. So AN is bigger than A capital N for all N bigger than capital N. Thus, we have A little n is bigger than L minus E. Okay, so this gives that we know L minus E is less than, or L minus epsilon, L minus AN is less than epsilon, since AN is less than or equal to L, okay? And consequently, we can say that the absolute value, because this difference could be negative, is less than epsilon when little n is bigger than capital N. And then therefore this is the definition of convergence. So AN approaches L. Okay, and the proof is similar if you assume it's decreasing. It would just be AN has a greatest lower bound, we call it L, and then greatest lower bound, then for epsilon greater than 0, L plus E is not a lower bound. And it would actually be a good exercise for you to kind of take this proof and look at the corresponding version if it is decreasing and how things would change. Also, if the proof here is a little bit confusing, I recommend trying to draw this as a picture. Okay, the picture might give this a little bit more meaning, so try it on your own, and then if you have questions, make sure to ask in class.